Hello friends, welcome to Shiksharthi. Hello friends, welcome to Shiksharthi. In this session, we shall be discussing some examples on rational inequalities. So let's start. Now the prerequisite for this session is you should have done our first session on the basics of rational inequality, wherein we have talked about fx divided by gx being greater than 0, and we have also talked about fx divided by gx being less than 0. So using whatever basics or concepts that we would have discussed in the earlier session is what we are going to use it here on the examples that are on the screen. Okay, so the first example that we are talking about is, so let's say this is the first example, and this is the second example that we have taken here. So if I say that phi x, I'm assuming that phi x is equal to x divided by x minus 1, and then I need to solve phi x greater than 1. So in this case, what is the domain of phi x? Is nothing but the domain of x. So the domain for x intersection with the domain for x minus 1. And in addition to this, x minus 1 should not be equal to a 0. So when you solve this, the domain for x is real numbers, the domain for x minus 1 also is real numbers. When you take the intersection of real numbers, you get the answer as real numbers. But in that case, the domain elements should not contain x is equal to 1. So the domain of the domain of phi x is minus infinity to 1, which is plus 1, union plus 1 to plus infinity. Okay. Now when we are solving this, as discussed earlier, so this is the basic that you talk about. This is the first thing that we do. The second thing that we do here is we divide this entire discussion into two parts, wherein the first part would be if the numerator is positive and so is the denominator, and then you take this with the intersection of phi x, the domain of phi x, then we get the total answer, we get the solution set. Second case here is when the numerator is negative and so is the denominator. In that case, phi x would be positive, and then you take the intersection of the domain of phi x, which is just like saying taking the intersection of all the three. So the best way here is, maybe you can draw a diagram. So the diagram says that, now which diagram am I talking about? You can just draw a number line so that you're able to solve this. So let's say this point is 1, this is 0. In one case we want x less than 0. In the other case, x should be less than 1. And the third thing here is we need to take this with the intersection of the domain of phi x, which is other than 1. You have all the real number values. So when we take the intersection of all the three, we see that this area is the area common to all the three. So we would say eventually the answer is x less than 0 from this side, union with the answer that you would get from this side. So let us see the answer that we get from the other side. What is the answer? So the answer that we are getting from the other side is, so again let us draw this. This is 1, this is 0, x is greater than 0. x is greater than 1, and then you need to take this with the intersection of the entire domain of phi x. So we see that the area that is common to all the three. So we see that this is the area. This area, which area are we talking about? We are talking about x greater than 1. So this is the final answer that we get from here. So when we solve this, what is the solution set that we are getting from here? We are getting the solution set which is a union of the two cases that we had made. So your learning becomes complete only when you take examples to the two cases that you would have taken. Okay, now in the second case that we are talking about here is the second example. So now if we wish, we can save time, or if you want to solve it independently, let us solve it independently also. We know that the domain of phi x, we have assumed that phi x is equal to x upon x minus 1. So the domain of phi x is nothing but minus infinity to minus 1 union minus infinity to plus 1 union plus 1 to plus infinity. Please mark the usage of the brackets. So once this basic thing is done, then we make two cases as discussed earlier, and the two cases would be, the first case is when the numerator is negative and the denominator is positive. This, when we take this with an intersection with the domain of phi x, we get the solution set from the left hand side, which is this case. The other case here is when x is greater than 0. In that case, the denominator should be negative. This, when we take it with the intersection with the domain of phi x, we get the other case. Both these cases are mutually exclusive. So when you are getting to the final solution set, you need to ensure that you take the intersection of all the three. So for this, now let us plot the diagram. So let us make a diagram here. A fairly easy diagram to draw, a number line. So one is, the first case is when x is less than 0, which is a line, arrow to arrow. Second is x minus 1 is greater than 0, which is just like saying x is greater than 1. And then you take this with the intersection, you take this, these values, and then you take this intersection with the domain of phi x, which is all real values except for 1. Now you would see that when we take the intersection of the values here, what are the areas that are common to all the three? The areas that are common to all the three. Okay, so when I take this and when I take this as an intersection, so is there any area which is common to all the three? So this is the area common to these two. This is the area which is common to these two. So you see that you do not get any area which is common to all the three. Okay, let us see the right hand side now. 0, 1, x is greater than 0. Okay, x is less than 1, and then x is all real numbers except for 1 is what we are taking, except for 1. Now we are interested in the area that is common to all the three. So the area that is common to all the three here is, can I say this part, which is just like saying x is greater than 0 and less than 1. is the final solution set that you get from here. Now, these are two inequalities, these are two examples of inequalities wherein these two are mutually exclusive to each other. So if I were to take a final take here, the final take here is if I combine all these values, I mean if I take this value, if I take this value, if I take this value, this should give me the domain of phi x. Does it give me the domain of phi x? It gives me all such values of phi x except for x is equal to 0 and x is equal to 1. So why doesn't it give me a value of phi x is equal to 0? Because phi x when becomes equal to a 0, it becomes an inequality. It becomes an equality. Phi x greater than 0, phi x less than 0 is the inequality aspect. So here we are talking about domain. So when I combine these values, we are getting the domain of phi x, and along with this we are supposed to ensure that phi x should not be equal to 0. I hope you would have got what I hinted at. So these are the two examples of inequalities from where you are having a higher level learning now, which is the next level of learning, which says that if I combine these two mutually exclusive inequalities, wherein in one case phi x is greater than 0, phi x is less than 0. So if I combine both these examples should have all the values which are the domain values of phi x, along with phi x should not be equal to a 0. And incidentally, when we were plotting this graph, so we would have seen that 0 was something which was always a part of the domain of phi x. But since phi x is not equal to a 0, we will have to check when phi x cannot be equal to a 0. So phi x cannot be equal to a 0 for x is equal to a 0. So eventually, if I combine the answers for both of these, I would say x belongs to real numbers except for x is equal to 0 and x is equal to 1. I hope you will be able to practice this to the best of your spirits and take this learning to the next level.